In the previous video, we covered net force analysis, and then we had a couple of examples. One example, we had equilibrium state system, and in the other example, we had an accelerating system. And it was shown that it doesn't matter whether you have equilibrium system or you have an accelerating system. Just follow the steps in force analysis, and it's just a matter of knowing when to set Fnet to 0 and when to set Fnet to MA. Again, you set Fnet to 0 for equilibrium system that is either static or moving at constant velocity, uniform motion. And if there's acceleration, you set the net force to MA, you have an accelerating system. Let's finish up our discussion on force and motion by looking at a couple of more examples. So let's have sample problem number 3. You have a bust, 5 kilograms in mass. The bust is suspended by 3 strings as shown in the figure. The tension in the left string is 23.1 newtons. Determine the tension in the middle string. So you have a bust suspended by 3 strings. The mass of the bust is provided, 5 kilograms. 3 strings. The left string has a tension of 23.1 newtons, and the string is oriented 45 degrees with respect to the vertical. The middle string is vertical, and the right string is also diagonal, 45 degrees with respect to the vertical. Determine the tension in the middle string. So what is the tension in this string? So we are provided with mass of the bust, 5 kilograms. Knowing the mass, we know the weight magnitude of the bust. Weight magnitude is just mg. G again is 9.8 meters per second squared. So 5 times 9.8 will give you 49 newtons. The tension in the left string is 23.1 newtons. Let that be T1. So the tension in the left string is T1. Follow the steps in net force analysis to determine the tension in the middle string. So let the tension in the middle string be T2. So determine T2. So following the steps in force analysis, identify, draw the figure. If no drawing is provided, there's already a drawing or figure provided by the problem. So we go on to the next step. Next step, identify the forces present in the system. We have already identified 3. We have weight of the bust. Weight is always vertically downwards. And then we have T1, the tension in the left string. Tension is always a pulling force. So the bust is being pulled by the string in this direction. You have tension T1. And then we identified T2, the tension in the middle string. So tension in the middle string, you have T2. Again, tension is pulling force. So the bust is being pulled by the string in this direction. And then you have a third string, the right string, let that be tension T3. You have the forces present in the system. In identifying the forces present in the system, we have drawn the free body diagram, analyzed the free body diagram, using either F net is equal to 0 or F net is equal to MA. The bust is simply hanging, suspended by the three strings, so the bust is in static case, static equilibrium. So we set the F net to 0, and there's only one object to consider, the bust. So there's only one free body diagram to analyze. For that free body diagram, again, static equilibrium, F net is equal to 0. And F net is summation of all the forces acting on the object, in this case, the bust. So summation of weight, tension 1, tension 2, tension 3. And the summation is equal to 0. And again, we are talking about vector quantities here. So we use component method to analyze the equation. We have the x component and we have the y component. So first, x component of f net is f net x component of 0 is 0, weight is vertically downwards, no x component, tension T1 is diagonal, angle is 45 degrees, the x component is opposite the 45 degrees, negative direction. So minus T1 sine 45. T2 is vertical, no x component. And T3 is also diagonal, 45-degree angle. The x component of T3 is opposite the 45 degrees and positive x direction. So plus T3 sine 45. We see that T3 magnitude is just equal to T1 magnitude. And we know T1 to be 23.1 newtons. So from X component, we get T3, but that's not what we are looking for. We are looking for tension in the middle string. We are looking for T2. So we move on to the Y component. Y component of F net, you have F net Y component of 0 is 0. Y component of weight is vertical, negative direction, so minus W. T1 is diagonal, 45-degree angle. The Y component is adjacent to 45 degrees, positive direction, so plus T1 cosine 45. T2 is vertical, positive direction, so plus T2. And T3 is diagonal, 45-degree angle. The Y component is adjacent to the 45-degree angle, positive direction. So plus T3 cosine 45. We get 0 is equal to minus weight plus T1 cosine 45 plus T2 plus T1 cosine 45. We replace T3 by T1 because from the X component, we know T3 is just equal to T1. Isolating T2, we get T2 is equal to weight minus 2 T1 cosine 45. We know weight, we know T1. The only unknown is T2. We are able to calculate T2 to be 16.332 newtons. And now we have sample problem number 4. A box is sliding along a slippery horizontal floor at a constant speed of 3 meters per second. It encounters a rough patch on the floor. If the coefficient of kinetic friction between the box and the rough patch is 0.5, Determine how far the box will travel before coming to a stop. The mass of the box is given to be 1.5 kilograms. And you are provided a figure. You have a box sliding on a slippery horizontal floor at constant speed until it reaches a rough patch on the floor. There is kinetic friction between the rough patch on the floor and the box. The kinetic friction will cause the box to slow down. Therefore, the speed or the velocity of the box will no longer be constant as it is sliding along the rough patch on the floor. The coefficient of kinetic friction between the box and the floor, the rough patch on the floor, is 0.5. Determine how far the box will travel along the rough patch on the floor until it comes to a stop. The mass of the box is given to be 1.5 kilograms, and knowing the mass, we know the weight magnitude of the box. Weight magnitude is just mg, which gives us 14.7 newtons. The coefficient of kinetic friction between the box and the rough patch on the floor is 0.5. As far as the rough patch on the floor is concerned, the initial velocity of the box is 3 meters per second, positive x direction. Eventually, because of kinetic friction, the box will come to a stop. The final velocity of the box is 0. Determine the distance traveled by the box on the rough patch on the floor. Now, we know initial speed and final speed. We don't know x. We don't know the acceleration of the box. We don't know the time of travel. So, there's not enough information for us to do kinematics to determine the final answer, x. We need at least one more variable. We either need to know the time of travel or we need to know the acceleration to be able to use kinematics to answer the problem. Fortunately, we can use force analysis to determine the acceleration of the system. And that's what we'll do in this example. We'll first do force analysis to determine the acceleration. And then from there, we do kinematics using the acceleration that we had calculated. So, with the drawing provided by the problem, identify the forces present in the system. We already know the weight of the box. Weight W is always vertically downwards. The direction is downwards and we know the magnitude to be 14.7 newtons. Because of the weight, the box is pressing into the surface, into the horizontal floor surface. The floor will react by producing normal force. The surface is horizontal, therefore the normal force is vertical. And because there is kinetic friction between the box and the rough patch on the floor, we have kinetic friction F sub K. Horizontal because parallel to the surface, and negative direction because the motion of the box is positive direction. Kinetic friction will always oppose that motion. It will always have direction opposite that of the motion. So motion is positive direction, kinetic friction is negative x direction. In identifying the forces, we have drawn the free body diagram. The system is accelerating, so we also need to include the acceleration of the system. The motion is positive direction, eventually coming to a stop. The object is slowing down. We have deceleration. motion is positive direction. For there to be deceleration, the acceleration must be heading in the opposite direction. So the acceleration A of the box is negative x direction. Analyze now the free body diagram. Since there is acceleration, we set F net to ma. And again, only one object to consider, so there's only one free body diagram to analyze. So F net is equal to ma. F net is equal to summation of the forces acting on the system. So you have weight plus normal force plus kinetic friction. And once again, use component method to analyze the equation. So we have x component. X component of F net is F net x. X component of acceleration A. A is horizontal negative direction, so minus ma. Weight and normal force are both vertical, so no x component. Friction is horizontal negative direction, so minus F sub K. This gives us MA is equal to F sub K. Kinetic friction magnitude is constant at mu K N. Therefore, A is just equal to mu K N over M. We know mu K, we know M. We need to determine the normal force magnitude N. So we move on to the Y component. So Y component of F net is F net Y. Y component of acceleration. Acceleration is horizontal. No Y component. Friction is also horizontal. No Y component. The ones that have Y components are the weight and the normal force N. Weight is vertically downward, so negative direction. Normal force is vertically upward, positive direction. So we get F net is equal to 0 is equal to minus W plus N plus 0. Which gives us the normal force magnitude is just equal to the weight magnitude. And we know the value of the weight magnitude. So we replace N by W. All the variables now are known. We are able to calculate the acceleration magnitude, 4.9 meters per second. The acceleration is heading in the negative direction. So if we now put this back into vector form, the acceleration is equal to negative 4.9 meters per second squared. Now that we know the value of the acceleration is constant at negative 4.9 meters per second squared, the box is undergoing uniform acceleration. You have four equations to choose from. One of the equations of uniform acceleration is v squared is equal to v naught squared plus 2ax. If you plot in the known values, the only unknown is x. We are able to calculate x to be 0.918 meters. In this problem, we used net force analysis to determine the acceleration, and then we performed kinematics analysis. In some other problems, you might have to do the opposite. First, you use your kinematics to determine the acceleration, and once you have the acceleration, you perform force analysis. So please take note of that. And that's it for now. That's it for our discussion on force and motion. So thank you for watching.